Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Dragonfly mission, soaring through Titan's alien skies. In the expansive frontier of space exploration, the Dragonfly mission stands out as one of the most ambitious and innovative undertakings in modern planetary science. This mission, spearheaded by NASA and part of the New Frontiers program, aims to explore Titan, the largest moon of Saturn, using a rotorcraft lander. Dragonfly represents a significant leap forward in our quest to understand the chemical and prebiotic processes that could give rise to life in the outer solar system. Titan has long been an object of fascination for scientists. With its thick atmosphere, surface lakes, and rivers of liquid methane and ethane, it presents a unique environment that, while vastly different from Earth, shares some intriguing similarities. Titan's dense, nitrogen-rich atmosphere and organic-rich surface make it a prime candidate for studying the complex chemistry that may lead to the formation of life. Dragonfly is designed to take full advantage of Titan's unique environment. Unlike traditional landers or rovers, Dragonfly is a dual quadcopter, a type of drone that can fly across Titan's surface, providing unprecedented mobility and access to diverse geological and chemical environments. This ability to fly is crucial because Titan's surface is varied and potentially hazardous. Some regions are covered with dunes, while others have large bodies of liquid hydrocarbons. By flying, Dragonfly can avoid obstacles and sample a wide range of sites, enhancing the mission's scientific return. The mission's objectives are ambitious. Dragonfly will carry a suite of scientific instruments designed to analyze Titan's atmosphere, surface, and subsurface. These instruments include mass spectrometers, gamma-ray spectrometers, meteorology sensors, and cameras. One of the key goals is to investigate the chemical composition of Titan's surface and atmosphere to understand the processes that produce complex organic molecules. These studies could provide insights into the prebiotic chemistry that might lead to the emergence of life. Dragonfly's journey to Titan is a testament to the advancements in aerospace engineering and planetary science. Scheduled for launch in 2027, the spacecraft will embark on an 8-year journey to reach Titan, arriving in 2034. The mission plan involves a series of flybys of Earth and other planets to gain the necessary speed and trajectory to reach Saturn's moon. Upon arrival, Dragonfly will deploy its rotorcraft and begin its exploration, leveraging Titan's low gravity and dense atmosphere to make long flights and detailed surveys. One of the most exciting aspects of the Dragonfly mission is its potential to explore the habitability of Titan. While Titan is much colder than Earth, with surface temperatures around -179 degrees Celsius, it possesses many of the chemical building blocks necessary for life. Dragonfly will search for prebiotic chemical processes in the moon's atmosphere and on its surface, seeking to answer fundamental questions about the origins of life and the potential for life elsewhere in the solar system. Dragonfly will initially land in the Shangri-La Dune Fields, an area rich in organic materials. From there, it will make a series of flights to explore different regions, including the Selk Impact Crater. Impact craters are particularly interesting because they expose materials from beneath the surface and can create environments where liquid water might have existed temporarily. By studying the composition and structure of these regions, Dragonfly will help scientists understand the chemical and geological history of Titan. The Dragonfly mission also represents a significant step forward in the use of autonomous systems for planetary exploration. The rotorcraft will need to navigate Titan's complex terrain without direct input from Earth, relying on sophisticated onboard systems to make decisions about where to fly and land. This autonomy is crucial given the vast distance between Titan and Earth, which makes real-time control impossible. The technology developed for Dragonfly could pave the way for future missions to other distant worlds. The mission's scientific instruments are designed to answer key questions about Titan's environment and its potential for prebiotic chemistry. The mass spectrometer will analyze the composition of Titan's atmosphere and surface, looking for organic molecules and other compounds. The gamma-ray spectrometer will measure the elemental composition of the surface, providing insights into the geological processes that have shaped Titan. Meteorology sensors will study the weather patterns and atmospheric dynamics, while cameras will capture detailed images of the surface and landscape. Dragonfly's ability to fly across Titan's surface opens up new possibilities for exploration. Unlike rovers, which are limited by the terrain they can traverse, Dragonfly can fly over obstacles and cover large distances quickly. This mobility will allow it to sample a diverse range of environments, from the icy crust to the organic-rich dunes and potential cryovolcanic features. Each flight will be carefully planned to maximize scientific return while ensuring the safety and stability of the rotorcraft. One of the mission's primary scientific objectives is to study Titan's organic chemistry. Titan's atmosphere is rich in methane and nitrogen, and it experiences a variety of chemical reactions driven by sunlight and cosmic rays. These reactions produce a complex mixture of organic molecules, some of which may be precursors to the building blocks of life. By analyzing these molecules and understanding their formation and distribution, Dragonfly will provide insights into the potential pathways for prebiotic chemistry on Titan. The exploration of Titan by Dragonfly will also contribute to our understanding of the broader context of the solar system. Titan is often compared to a frozen version of early Earth, and studying its chemistry and geology can provide clues about the conditions that existed on our planet before life emerged. By comparing Titan's environment with those of other moons and planets, scientists can develop a more comprehensive picture of the processes that govern the formation and evolution of planetary systems. In addition to its scientific goals, Dragonfly is expected to inspire a new generation of scientists, engineers, and space enthusiasts. The mission's innovative design and ambitious objectives capture the imagination and highlight the possibilities of human ingenuity and exploration. As Dragonfly takes flight over Titan's alien landscapes, it will provide a powerful symbol of humanity's quest to explore and understand the universe. Dragonfly's exploration of Titan is also significant for its potential to inform future missions to other icy moons and distant worlds. The technology and methods developed for Dragonfly could be adapted for missions to Europa, Enceladus, and other bodies with subsurface oceans and complex chemistries. These missions could search for signs of life or prebiotic chemistry, building on the discoveries made by Dragonfly on Titan. The mission's success will depend on overcoming a variety of technical and engineering challenges. Titan's dense atmosphere, low gravity, and cold temperatures create a unique set of conditions that require specialized equipment and systems. The development of Dragonfly's rotorcraft, power systems, and scientific instruments has required innovative solutions and extensive testing. The mission team has worked to ensure that Dragonfly can operate reliably in Titan's harsh environment, conducting detailed simulations and tests to prepare for every eventuality. As Dragonfly prepares for its launch, the mission team continues to refine the science and exploration plan. Each aspect of the mission is carefully considered, from the trajectory and landing site selection to the sequence of flights and scientific observations. The goal is to maximize the scientific return while ensuring the safety and success of the mission. This meticulous planning reflects the complexity and significance of the Dragonfly mission and its potential to transform our understanding of Titan and the outer solar system. The Dragonfly mission also has implications for the search for life beyond Earth. While Titan's surface conditions are harsh, its subsurface ocean and organic-rich chemistry make it a compelling target for astrobiology. By studying the processes that produce complex organic molecules on Titan, Dragonfly could provide insights into the potential for life in other icy moons and planetary bodies. The potential discoveries from Dragonfly could have far-reaching implications for our understanding of life's origins and the conditions necessary for its existence. By exploring Titan's unique environment and studying its chemistry, Dragonfly will provide valuable data that could inform the search for habitable environments in other parts of the solar system and beyond. The mission's findings could help scientists identify new targets for exploration and develop strategies for detecting signs of life on distant worlds. In conclusion, the Dragonfly mission represents a bold and innovative approach to planetary exploration. By leveraging the unique environment of Titan and using a rotorcraft lander, Dragonfly aims to answer fundamental questions about the chemistry and geology of this intriguing moon. The mission's ambitious goals, cutting-edge technology, and potential for groundbreaking discoveries make it a landmark in the history of space exploration.